Okay, so this video is going to be a tutorial on how to do combustion analysis problems. And I sometimes kind of like to call combustion analysis problems as stoichiometry with a twist. So, the first thing you want to know is, draw on this, when you're doing a combustion analysis problem, you always want to remember a few things. You are going to sometimes have a hydrocarbon, which is like some number of carbon or some number of hydrogen, plus the other reactant will always be oxygen gas. And in this case, you're always going to make carbon dioxide and water. Now, sometimes this hydrocarbon also might contain some oxygen as well. So sometimes you could also see it like this. Another way, sometimes this hydrocarbon could also have some nitrogen. That's not sodium. Let me not make that. So I'll put like an NB. And again, it's plus oxygen gas. But if this is happening, usually you're also going to have some like maybe nitrogen monoxide as a product. So you'd have another product with N and O in it. So the main thing to take away from this is when you're doing a combustion analysis, the other reactant is always going to be oxygen gas with some hydrocarbon compound. And if it just has C's and H's or C's, H's, and O's, your products are always going to be carbon dioxide and water. Now, when you also do combustion analysis problems, what they're going to give you is they're going to give you the grams or the moles of product form. And you're actually going to have to work backwards to determine, what's the empirical formula of this compound. There's easy ones and hard ones. If this very top one, this is going to be considered an easy one. These bottom two are going to be considered hard problems. So basically, I'm just going to go ahead and go to this worksheet that you're going to be provided in class. And you're going to see the differences between the easy and the hard. And I'm going to go ahead and just work one of each. But the number one thing to remember is you can take these guys back to, if you're in grams, your plan is always go grams to moles. And then you can always do your mole to mole ratio. And then we'll go back to moles. And then we'll go from there. So, okay. Scroll down to this page. So, just so you can kind of see, question 1 and 2 is with, it's like what I just showed you, but it was with B and H, and so it made B2O3. And question 2 is with silicon and hydrogen, and so it made SiO2. But what you should notice is, again, oxygen's a reactant, and then water's a product. So those are like the same, but again, to stick with the ones that I was just going over, I'm going to do question 3, and I'm going to do question 4. So question 3 is going to be considered an easy problem, while question 4 is going to be considered a hard problem. And then we'll kind of compare and contrast the differences. So I'm going to give me some space here to work this. Okay. Now, there's another thing about AP is they're going to give you lots of words and you have to just kind of dissect them. So naphthalene is a hydrocarbon, so hydrogen and carbon. It's used for mothballs. A sample was burned in oxygen to produce 1.100 grams of carbon dioxide and 0.1798 grams of water. And then it tells you the molecular mass is 128 and what is the empirical and the molecular formula for the compound. So, what do we actually know? We know that we made 1.100 grams of CO2, and we also know we made 0.01798 grams of water. And again, this is why this one is an easy one. You have to just keep in mind all the carbon dioxide, what we'll do is we'll take it grams to moles of carbon dioxide, and then all of the carbon, just carbon, came from this carbon. So what we can basically just say, we'll go ahead and see it, is we're going to assume all the moles of this carbon came from the moles of that carbon. We're going to make that assumption. Same thing for the water. We're going to take water grams to mole. Then we're going to do the mole to mole ratio and say all of this hydrogen from water came from this hydrogen here. So let's just do that. Keep that in mind though. So I'm just doing train tracks because it's easier for me. So basic stoic, starting off, grams of CO2 has to go on bottom, and then that's going to be for every 1 mole of CO2. Depending on the periodic table you use, I know carbon dioxide is 44.01 or 11. Like I said, depending on the periodic table you use, 1 carbon plus 2 oxygens. Hopefully that's not news to you. And so from here, we canceled out grams of carbon dioxide. Now, you have to say, okay, well, for every 1 mole of carbon dioxide, how many carbons are actually present inside the molecule? So it's like we're diving into the compound. Well, your answer is, how many do you see? You just see 1. So there's 1 mole of carbon. And then we're going to we get to stop there. So that is going to give us, we're just going to do, using just a simple calculator on my phone to divide this. I get 0.0249. And it's 99. I'm just going to keep, usually when we're doing the empirical, because it says empirical molecular, we're just going to keep kind of everything. I would keep it if I had the calculators. I'd keep all the numbers here. Okay, now we're going to do the second one. Same process. So grams of water has to go on bottom. And you'll probably start to memorize water as 18.016. We use it all the time. But again, you add 2 hydrogens plus 1 oxygen, you're going to get that number. And that's always in 1 mole of water. Those still have to match. Now, this is the one that is always going to be tricky when you're doing the water. Because for every 1 mole of water, how many hydrogens do you have? There are 2. So this time we actually write there's going to be 2 moles of, not water, 2 moles of hydrogen on top. So again, think back, all of this hydrogen came from that hydrogen. So when we work backwards, we have to take that 2 moles of hydrogen in water into account. And then once we do that, the moles of water cancel. And now we're going to go ahead and multiply across and divide, or whatever your favorite way is. But I'm doing 0.1798 times 2 divided by 18.016. And I get that 0.01996, and that would be moles of hydrogen. Okay, so now that we have moles of each, now we can actually take into account we can find the empirical, and then we can use this molar mass to find the molecular. So if you remember empirical formula, it was percent to mass, and then it was mass to mole, which guess what, we're already in moles. And then you have to divide by the smallest. Oh, and that's getting really hard to write there, so I'm just going to say it. Divide by the smallest and then multiply till whole. So out of these 2 numbers, we're going to divide by the smaller one, which is the 0.01996. Okay. The hydrogen's going to come out to be 1. And this carbon comes out to be 1.25. And this one comes out to be 1. So in this case, you're not done. You can't have C 1.25 and then H 1. That's not allowed. So remember the last step, after you do percent to mass, mass to mole, divide by smallest, then you're going to multiply till you have a whole number. So our whole number in this case we're going to want is, you have a 0.25, so we're going to multiply both of them by 4. So when I do that, I get C, 1.25 times 4 is going to be 5, and then H was a 1, so now it's going to be a 4. So you're going to get C5, H4. So that would be the empirical. Okay. Then the molecular formula is, remember, we are always going to compare to the 128, so I'm going to round for this purposes. 5 carbons at 12 apiece, I'm going to round, is 60, plus 4 hydrogens at 1 apiece is 64. So if you remember, the empirical molar mass is 64 grams per mole. The molecular is 128 grams per mole. So if I'm trying to get the molecular formula, how many times does 64 go into 128? That's just an easy 2. So my molecular formula is going to be C10. I should have to double it. Times it by 2, times it by 2, H8. And that would be my molecular formula. And usually it's not going to go all the way and ask you about the molecular. It's going to stop at the empirical formula and ask you what could be the formula for this hydrocarbon. But that's always your same pattern. Now, like I said, that's the easy one. And now we're going to do the harder one, which is number 4. Give it some good space. Okay. Alright, right, so this is the hard one. It's going to ask us from empirical and molecular again, but we're going to have a lot more math to do. And so here's why. You've got butyric acid, contains CHNO. It's a component of rancid butter. Burning 4.40 grams of butyric acid in excess oxygen yields this much CO2 and this much water, and those are the only products. What's the empirical molecular? The reason why this one is more tricky, so I'm going to zoom in. In the last example, all of the carbon came from carbon dioxide. All of the hydrogen came from water. But the reason why this one is tricky is now we have this oxygen in this compound, but we have the oxygen here. So the oxygen here and here do not solely come from that oxygen. It's that oxygen and that oxygen. So it's going to become a bit more tricky. So first of all, we have to actually just keep in mind for this example, we cannot just stop in moles. We're going to actually have to go grams to mole, back to grams of like C, and then you have to do the H and you have to do the O's. And we're going to have to do the O's for both. Or actually, no, sorry. We're going to just do the grams for C and H because that doesn't make sense because we're going to have both oxygens here. Sorry. We're going to do the grams for C and the grams for H, and then we're going to add those together, and we're going to have a grams here. And then what we know is we know our actual sample was 0.440 grams. So when I take this number and then this number and I subtract, that should be the amount of grams of oxygen in my sample. So that's my plan. Let's go ahead and get this going. So we're going to start off the exact same way as before. 0.360 grams of water. We're starting off the exact same way. You're going to get used to their molar masses. Plain old molar mass for carbon dioxide. Then we do our mole to mole ratio. For every 1 mole of carbon dioxide, there's 1 mole of carbon. But like I said, now we're actually going to go further. We're going to go to grams of carbon. So 1 mole of carbon has 12.01 grams. Periodic table. Okay, I'm going to set up the bottom one as well. Just like we did in the last example. Grams of water. That's how many moles of water you have. But for every 1 mole of water, again, this is the tricky one because how many hydrogens? You have 2. And then for every 1 mole of hydrogen, it's 1.008 grams of hydrogen. Okay, so we're going to go ahead and do this math. So 0.882. Sometimes the numbers can look very wacky. Times 12.01. Divided by 44.01. Yeah, 0.24 grams. And there was like 0.69. I would keep everything again if I had a calculator, big calculator. All right, bottom one, 0.360 times 2 times 1.008 divided by 18.016. I'm getting 0.04. 040 grams. Okay. So this is where, like I said, the kind of slightly tricky part comes into play. Is we knew that they're out of this compound here, out of the 0.44 gram sample, we know that 0.24 is carbon, and we know that 0.040 gram is hydrogen. So now we need to know how much oxygen was in there, so we're just going to subtract. So I'm going to do this over here off to the side. 0.440. Zooming in. Minus 0.24 minus 0.040. We're going to do that math. Just a little subtraction. 0.440 minus 0.24 minus 0.04. It gives us 0.16. And that amount left over is the amount of oxygen in the compound. So now what we get to do is we get to do the empirical all the way from basically the beginning. So these are my 3 numbers right here. So again, remember when we do the empirical and molecular, percent to mass, mass to mole, divide by smallest, multiply to whole. In the easy example, we were already in moles, so we just got to divide by smallest and then multiply to whole. This example, we're all the way in grams, so we're just going to have an extra step, but it's okay. See if I can squeeze. I'm going to actually make a little bit of space here, so I'm going to erase this. Leave my numbers up here so don't forget. Okay, so now we're going to just have to go back and start again. So grams of carbon, grams of hydrogen, grams of oxygen. Now I just do my basic, again, empirical percent to mass. I'm already in mass, mass to mole. So it kind of seems repetitive, but I'm going backwards. I'm going back to moles. So I'm dividing by the molar mass. And then 16 grams. Oxygen, 1 mole. So this is just like your basic stoichiometry going back. Like I said, I like to call combustion analysis stoich with a twist. So this one comes out to be 0.01998. Next one, 0.03968. And this one just comes out to be 0.01. So, and all these are in moles of their, moles of carbon, moles of hydrogen, moles of oxygen. So now we divide by the smallest. Now that I don't need these numbers anymore, I'm going to give myself some more space again. So divide by the smallest, which happens to be 0.01. That's going to give us just going to be 1 mole of oxygen. Okay. The 0.03968 is going to be very close to the number 0.01. You get 3.968. That's definitely close enough to 4. Okay. And then the top one, again, it's going to be super close to 2. But if I go ahead and actually type this in, it's 1.998. So yes, that's close enough to 2 moles of carbon. So this means my empirical formula is C2H4O. That would be my empirical formula. Okay. And then my molecular formula I'm going to compare to the molar mass. It says it's 88. So I need to find the molar mass of my empirical. So 2 carbons, 2 times 12, plus 4 hydrogens, which is just 4, plus 1 oxygen is 16, gives me 44. This molar mass is 44 grams per mole. And just kind of like the other one, how many times does 44 go into 88? 2 times. So my molecular formula over here is going to be double everything. So it's going to be C4, H8, and O2. Okay? So that's why that one was hard. It was super a lot of work. And you're only going to have to do that if your compound is not made up of C's and H's. But I will say for the most part, AP test is going to ask you only about the easy one. So hopefully you can refer back to this video and follow through the steps to basically finish the rest of this worksheet. Okay, and that is all for combustion analysis.